Hello students, my name is Tayfun, and in the previous sessions we have been delving into the world of shellcode development and assembly programming. And we learned about crafting shellcodes, addressing bad characters, utilizing relative addressing, and refining our code to ensure efficient execution. In today's lecture, we are about to embark on an exciting journey. We will focus on assembling and linking our code, ultimately creating a piece of C malware. But that's not at all, and we are taking things a step further by injecting our carefully crafted shellcode into our C application. So this integration promises to be a fascinating intersection of theory and practical implementation. So fasten your shellcodes because we are about to explore the process of turning concepts into tangible, executable code. Now let's dive into the world of assembling, linking, and injecting a shellcode into our C app. So we've reached an important. Let's actually close this, open a new tab. Yeah, we have this here. So we have here we have reached an important juncture in our learning journey. As you recall, we have been carefully constructing a shellcode that encompasses a series of intricate steps, and one of these steps involves manipulating memory addresses. So in our current phase, we are dealing with address of this malware injected string. So this address is expertly pushed onto the stack and the pivotal area of memory used for temporary data storage. So subsequently, we perform a pivotal operation, which is the pop RSI here. So this instruction takes the address we've placed on the stack and seamlessly transfers it into the RSI register, so a specialized storage location within the CPU. So by executing the pop RSI here, we facilitate efficient access to the address now stored in the RSI register. So this action will prove crucial as we proceed to wield this address in this next steps of our shellcode development. And remember, each step contributes to the intricate dance of assembly programming, resulting in culmination of our meticulously designed shellcode. Now let's actually, so we have compiled this assembly code. We have assembled it, linked it in previous lectures, and as you can see here, when we run this, it prints out in the terminal that the malware is injected. So this is just a print function here. Actually, we don't have any malware in it, but we can manipulate this in a way that we can here, like the buffer overflows and other privilege escalation attacks. Now, what we're gonna do is we will create the shellcode, since we have already have this assembly program here, runnable here. So we will again use this long cmd long terminal command here, obj dump m intel d hello here, the hello, and as we write this, I will explain this line by line. Let's actually first write it down here. 090. Oops, actually, let me fix this microphone here. Or can you hear me? Yeah, perfect. Now, what we're gonna do is we will use the 9AF, and here pipe grep v. So we don't want to see any files here. Cut or header information. So f2d cut f1 f17d here, trs here, and tr t set s here, and $, $g set s xg, and lastly paste the s. obj dump, not obj ump. Oops, and we also need to enter our program here. So hack it here, as you can see. And we got this cut option requires an argument. We actually have this here. So cut here, yeah. Yeah, I think, yeah, we need to make space here. Right. We got this error again, not this. Here, let's fix that also. And as you can see here, this is our shellcode. And as you can see here, we have something wrong in the shellcode because we need to add spaces between these quotes here. Also, I think we need to, no, we don't need this spaces here. Let's run it. And as you can see here, this is a valid shellcode. So if you're seeing this access without any values, hexadecimal characters, then this means there is something wrong with your shellcode here. And this is our shellcode here. Now, what we're gonna do is I wanna also explain this objdump command here. So this objdump m intel the hacked here, this part runs the objdump command on the file named hacked, and disassembles it using the intel syntax, and it provides a detailed disassembly of the binary. And we have grep 09af, and this filters the lines that start with the hexadecimal number followed by a colon, which are indicative of assembly instruction. And grep file here, this excludes the lines that contain the word file, possibly removing some header information from the output. And we also have this here, cut F2D. This extracts the second field. This is the actual assembly code using the colon as the delimiter. And we also have cut F17D with quotes here. So this extracts the first 2/7 fields from the output, which are usually the hexadecimal opcodes. And as you can see, we also have TRS with quotes. So this TRS, this squeezes multiple spaces into a single space, helping to standardize the format. And we also have this like double quotes here. No, double single quotes here. So this replaces tabs with spaces. And we also have set $G. So this removes any trailing spaces at the end of each line. And we also have sed s slashes a lot, and this replaces each space with this x to format the output in a way that's often used for shellcode. This is this, as you can see, that's it. And we also have the paste the lastly paste the s. So this this actually concentrates all the lines together to form a continuous string of formatted shellcode. So when you run this entire command together, it takes the disassembled machine code output from objdump, processes it through the series of transformations, and outputs as a string of shellcode in a specific format. So this formatted shellcode is then ready for use in your C or assembly programming. Now what we're going to do is we will create a new main.c here, or hacked tool here .c. And now what we're going to do is we will include the stdio h, include the string .h, and now we will create our main function. In this main function we will, oops, not this, here, in this main function we will firstly create our unsigned character, which we will name it our shellcode, and after that we will enter this output into our array here. So unsigned character array, code array, or actually let's make it shellcode array here. And with this, we will enter in the quotes here. Let's copy this from here, paste here, and semicolon. Now we will also print that the length of our shellcode. Printf the shellcode length. We will use D here, and after that we will actually use the new line after printing our shellcode length. So integer str len and code shellcode. Now that's it here. No, not here. Here. And now we will also use the integer, create a new function here, basically. And integer this here. And outside of this, we will write shellcode. And we will call this function. That's it. Now, this code is a C program that's designed to execute a shellcode, which is represented as a sequence of hexadecimal values. Now, let's break it down step by step here. So here we are using two includes, we are including two header files. So these are the preprocessor directives that include the necessary standard libraries for input output and string manipulation. And we also have this is the main function. This is the main function of the program where the execution starts. And here in this unsigned char shellcode, this line initialize an array named shellcode to hold our shellcodes. So the shellcode itself is carries of hexadecimal values that represent machine instructions, and it's stored as an array of unsigned characters, which is also we can call bytes. Now, here this part contains the actual shellcode represented as a hexadecimal values, and each pair of hexadecimal digits represents a byte of machine code. So the shellcode here performs a specific action, such as executing our syscall and printing the here malware injected string on the command line here. And we also have integer. So the print here. Before this ret we have print. So this line prints the length of the shellcode using this printf function. It calculates the length of the shellcode using the shellcode array using this str len and prints it as an integer. And we also have the integer ret, integer shellcode. So this line declares a function pointer named ret. So this function pointer is initialized to point to the memory address of the code array. So this effectively creates a callable function from the shellcode. And with this here, we are calling function pointed to by the ret pointer. And in other words, it executes the shellcode. So in summary, this C program acts as an executor for this provided shellcode, and it calculates and prints the length of the shellcode, converts the shellcode into a callable function using the function pointer, and then executes the shellcode. And this also allows you to test and observe the behavior of your shellcode within a controlled environment. Now what we're gonna do is let's actually compile this main here. Clear. Now we have this hacked tool.c here. Now in order to compile it, there's a simple command. We will use a gcc f no stack protector z exec stack here, and here we will hacked tool.c. Now we have some problem here. As you can see here, integer from incompatible pointer type integer. Let's see it here. So we got the type conversion error, but we can simply fix that easily here. Now, as I said, we have some type conversion errors here, and in this initial code, we were trying to calculate the length of the shellcode array using the str len, which returns a value of size t. However, we were trying to cast it into integer, which could lead to potential uses, especially when the length is larger than what an integer can hold. So in this corrected code here, what we're gonna change is we will change it to zu here, and here we will actually delete that, and we will use strlen here and const character here pointer, and after that we will enter code, shellcode. And that's it here. Our code is fixed. Now let's try this, and we got that error again. So integer from incompatible pointer type, integer pointer here, shellcode character, and we also have at the line 8 here, yeah, and we've got the same error here, but we changed this. So because it's actually our error was not raised here, but since we changed it, we did a good thing here, because if our shellcode was bigger than the size t of our integer, then we will get the error at this line 7. And now what we're going to do is we will fix that here. So we had some type of problem, integer shellcode here. So the problem is here. After that, yeah, and here. Now the problem should be fixed here, and as you can see here, our program is compiled and we can run it, a.out. Now let's run it again in the new line, and as you can see here, shellcode length is 55 and malware is injected. So fantastic, right? So you've wrapped now we have wrapped our lecture beautifully, and in the session we have covered a wide range of crucial topics, from the GMP shellcode, which we used here. Let's actually go here. So we use the GMP technique to explore new debugging styles with GDB and utilizing tools like Valgrind in previous lectures. So these insights are invaluable for anyone interested in shellcode and exploit creation. So by delving into these techniques and tools, you are equipping yourself with essential skills for creating efficient and secure code, as well as gaining deeper understanding of the intricate world of shellcode development. So I'm excited to continue this learning journey with you in our next lecture. Feel free to bring any questions, doubts, or ideas you'd like to explore further. Until then, keep up the great work, and I look forward to our next session.